Well, welcome everybody to the 2025 AI Literacy course. And thank you to Dr. Richards for kicking us off. That was a fantastic presentation to get us primed and ready to go for the rest of the week. So this is now our sixth version of this course that we've been doing every year. Our purpose of this course is to provide a fundamental, practical view of AI for future radiologists and radiologists currently in practice. So we are going to jump into this introductory presentation here. So my relevant disclosures include that I am the Artificial Intelligence and Radiology Education President and co-founder. I'm also get royalties from Meetings by Mail, and I'm the director of the Artificial Intelligence and Radiology course that's available through this program. And we have a really fantastic week of lectures that are going to be, I'm going to go ahead and turn this camera off, sorry. All right, so we have a fantastic week of lectures. We are going to be covering a lot of topics that we have seen before for some of you who have been part of this course in previous iterations, but we're also going to have some topics that are completely new to us. So we're going to be covering body imaging, chest imaging, breast imaging, and just had a fantastic lecture about AI and neuroradiology. And then we're also going to be having topics on the environmental impact of AI and video fluoroscopy, and we are going to have a vendor highlight at the end of the week for applications of AI in ultrasound with Echo Intelligent. Oh, there we go. And so we're very grateful to our partners this year. So we have been partnering with the Society of Advanced Body Imaging for the past 2 years. They've helped us to bring this program to a larger audience and are helping us to manage our enduring materials. And we're also very grateful to Philips, who is providing financial support for this course and is going to be supporting our in-person session at the Society of Advanced Body Imaging conference this year. So for those of you that are not members of SABI, I would highly recommend you considering to join. It is a fantastic organization, especially for anyone that's interested in the practical applications of AI in radiology, and specifically for anyone who is practicing and using a lot, or who's doing a lot of body imaging, so chest, cardiac, abdominal, GU. It's a really fantastic conference. And if you will be attending in person, we're going to have a session on Saturday. We'll get to that in just a moment here. So what we're doing with this particular session is that we are going to talk about the course objectives. We're going to go through some of the fundamental terms and methods of AI in radiology. And we're going to give a refresher on some of the basic concepts of statistics and data preparation that we'll be referring to throughout this course. So for this course, we have 10 lectures covering different topics and practical applications of radiology AI. This introduction to terms and methods is going to be laying the foundation for the different things that we're going to be talking about. We're also going to be presenting some of the subspecialty applications, and you've already gotten a taste of that. We'll talk about preparing for the future of clinical AI with our subspecialty applications. And we'll also talk about considerations for clinical integration. So this year we will not be doing a pre and post course evaluation. We're going to be doing something a little bit different. We are going to give you the opportunity to see what using AI as in a hands-on experience is going to be like. So we've worked with one of our developers here on site at UAB who has an AI augmented radiology education tool that we're hoping to give you the opportunity to demo on Friday. So we'll have more information on that closer to that date. So I think it's important to remember that the purpose of this course is that we are trying to provide a very practical view of AI and radiology. So we want to have this information available in an accessible way and in a clinically relevant way for all of our participants. We want to show the strengths and weaknesses of clinical AI. So we want to show not only what AI can do, but very importantly, we want you to come away from this course having a better understanding of what AI cannot do. And that's really important to the safe and appropriate application of AI in clinical practice. And we really want to have this foundational knowledge for our participants to be able to thrive and lead in the future of AI integrated healthcare. So something that is new for this course, we'll have a Future of AI and Radiology Roundtable at the Society of Advanced Body Imaging annual meeting. That's going to be in Nashville, Tennessee on Saturday, October 11th, from 11:30 to 12:30. So if you are attending this meeting in person, we highly encourage you to come join us for this roundtable. It's going to be a lot of fun. We're going to talk about how to bring AI into real world practice. We'll discuss different user experiences. And our goal is to show what the different perspectives of AI are from different people who are using it in practice. So we'll have medical students, we'll have residents, we'll have practicing radiologists, we'll have practice leaders all talking about how they view AI in practice. And we are also going to have this hands-on experience with the AI augmented learning radiology tool at the end of the week. So in summary, what this course is an introduction to the terms, methods, and applications of AI in radiology. This course is not a computer science course. It is not a statistics course. And very importantly, it is not an infallible look into the future of radiology and AI. So to get the most out of this course, I highly recommend that you focus on the basics. Highly recommend that you focus on these core concepts, learning them and building on them over the course of the different lectures, and concentrate on the practical and clinical applications of AI in radiology. So we're going to jump now into the introduction of AI terms and methods. And I do want to also mention, since we're coming towards the end of the hour here, if there's anyone that does need to get off of the Zoom, step away for any reason, these lectures are recorded. They will be posted to our YouTube page within 1 week of the course. So these materials will be available in an enduring fashion for anyone that's learning asynchronously or needs an update at a different time. So we have broken down our core competencies of AI and radiology into these 10 milestones, 10 key areas that we hope that you will have a better understanding of by the end of this course. So we're going to start with the AI terms and methods, the term hierarchy when it comes to artificial intelligence. So when we say artificial intelligence, this is a very broad catch-all term that we use to refer to a lot of different applications that are performing tasks that are very complicated that one might traditionally say would require human reasoning. But there are more specific terms within that umbrella that you may hear as well. Machine learning is a technique that can learn and adjust tasks. More advanced techniques like more advanced techniques like deep learning and neural networks are when you can get into these programs that can really start to mimic human reasoning and decision making. And these are using multiple layers and different nodes to make these decisions based on different inputs. So we have an example of a graphical representation of what that can look like in the bottom right corner, where you have different inputs, and then as it moves through these very complex networks, it's making small decisions across or along the way, and it eventually comes out with an output. But to develop an AI application, you require a lot of data. So that data can be broken down into your training, testing, and validation data sets. So the vast majority of your data when you're putting together or when you're acquiring data to train your algorithm is going to go into your training data set. So this is traditionally broken down into 60-20-20 when you're talking about training, testing, and validation. But if you're only doing training and testing, that would be in the range of about 80% to 20% of training to testing data. So the vast majority of data is going into training, and that is because you want to build up a very, very strong algorithm before you get into the stage that you're wanting to test it on new data. So training data is the data that is used to develop the algorithm. Testing is going to be how you see how the algorithm performs. And this is going to be the stop phase where you determine, okay, is this performing as well as I want to, or do I need to circle back, do a different technique, do some retraining, retesting, retraining, retesting. And this can take multiple phases to get the algorithm where you really want it to be. And validation is going to be the data set aside to see if the algorithm performs well on different data. And this can go even farther, that you have external validation, where maybe you have a different partner at a different hospital, or even a totally unassociated group that is running a validation on your algorithm using their own data. So this is data that the algorithm has never seen before. So you're challenging it to see if it performs well on a new set of data. And this is going to be where you start to find evidence of overfitting and underfitting. So these are some of the pitfalls that you can find with algorithms that when they're in development, They can get very, very good at finding patterns and making decisions on the data that they're trained on, but maybe they're taking shortcuts, maybe they're cheating a little bit, and they're making decisions based on the training data that is not really applicable to data that they would encounter out in the wild. So an overfitted algorithm is going to be one that's too highly trained on its own set of training data. And as soon as it's challenged with a validation data set or an external validation data set, it's going to perform very, very poorly. And on the other hand, you have underfitting, and this is when an algorithm performs poorly, even on its own training data. And this might be just due to insufficient training or poor data preparation. But even within its own data set, an underfitted algorithm is still not performing well. Algorithm bias is another very important pitfall that we have to consider. So AI patterns that are producing results in a biased way. So we touched on this very briefly in the lecture from Dr. Richards, but having insufficient diversity in the training data set can potentially perpetuate or create new biases and different health disparities in terms of how well the algorithm performs on different patient populations. And it's important to know with this is, or with algorithm training as it relates to algorithm bias, that an algorithm is only as good as its data. So an algorithm that is fed biased data, whether this is intentional or much more often, whether this is just unintentional and a reflection of this healthcare system or the culture or the region that this is trained in, it could reflect, it very well could reflect the underlying biases that are part of that healthcare system. And so this is a problem, especially for our black box applications, that we don't necessarily understand how the algorithm is making its decision. And it makes it more difficult to track these results over time and view these news or detect these potential new sources of bias. So to break this down into an example that hopefully would be relatively more understandable, if you can imagine a chest X-ray data set that is detecting cardiomegaly, and perhaps this is trained on a disproportionate number of male patients, and when you deploy it out in a broader population, you notice that disproportionately it's saying that female patients have cardiomegaly even when they're checked by a human radiologist and says, oh, this is a false positive. This patient does not have cardiomegaly. So maybe because of the training data, it's not recognizing breast tissue appropriately. Maybe there's other factors in the acquisition that are making it cause this, or that are having it to, or making it cause this error. But because there was not enough diversity in the training data set, and you're seeing this disproportionate number of errors, this would be an example of algorithm bias. So supervised, unsupervised learning are two different types of techniques when it comes to training AI applications. Supervised learning is one with human oversight, where the human determines the ground truth. It provides direct feedback into the AI results and helps determine different patterns. This is through labeled data sets and can be in anatomy segmentation. Whereas unsupervised data sets are ones that do not require human oversight. So the algorithm is organizing the data, extracting features, and learning patterns without necessarily requiring the human to provide insight or provide feedback during its training. And then you have the middle step where you have semi-supervised learning. This is where the algorithm extracts the data, but at some point in the training process, it gets feedback from the human user. So here we have supervised learning where the human is providing feedback to the algorithm who's developing patterns and producing the final result. So unsupervised is where the algorithm itself is developing these patterns, and then semi-supervised is where at some point in the process, the human is providing ground truth, providing the feedback to the algorithm before it's published. It's also important to remember that not all AI applications are specifically related to image interpretation. So actually, the vast majority of the AI applications that are available for use currently in the marketplace are not related to image interpretation. They're related to these upstream or downstream tasks in radiology. So Upstream AI would be related to would be algorithms that are deployed prior to image interpretation. So these could be related to image processing or image processing. They could be related to decision support. They may even be even further upstream. They might assist the referring provider, referring physician in determining what the appropriate study to order would be. And then we have downstream AI, and these are applications that are deployed after the image is interpreted. So these could be 3D reconstructions for surgery planning. They could be report optimization and different text-based applications for the radiology report. But this is just to remind you that not all AI applications in radiology are specifically related to interpretation. And generalizability is what you would consider the opposite of overfitting. So generalizability means an AI application can be applied appropriately to different types of patient populations in different regions on different scanners and performs well across all of these different environments. And as an example of this, so we have that same chest X-ray application. It's trained on this data set from Hospital A, which is this very large but homogeneous data set. But even when we deploy it in Hospital B and Hospital C, where we have a more diverse patient data set, it's still performing well and providing a correct result. And explainability is a user feature that is helpful for the human radiologist and the human clinicians, that it helps us understand what the AI is determining as an important feature to make its decision. So this is how we can help to avoid the black box, which, as we mentioned earlier, the black box would be the different uninterpretable processes that we, as the human user, can't really understand how the AI is making its decision. This is a very extreme example of this, that you feed in an image, the AI processes the image, and it just tells you cancer. Like, why does it say there's cancer or this patient has cancer? What in the image is causing it to make that decision? I couldn't tell you, but the AI says so, and I don't know why. So you can understand that that would cause a lot of concern if we didn't have any quality control steps for this, and we're making significant decisions for this patient's treatment uh, based off of something that we cannot understand. So some of the common explainability features that we see are heat maps, which highlight the area of interest. And there are some other methods as well, but that's probably one of the most common ones. And this is an example of what this can look like. So for an intracranial hemorrhage application, this would be a heat map showing a focal area of increased density in the head CT. For a pulmonary embolus application, this would be showing you a suspected pulmonary embolus in the left lung. And then you have one for non-mass enhancement in a breast MRI. And a very narrow or a very important concept to remember for the FDA or the FDA cleared AI applications that are currently out there is that most of these AI applications are very narrow in their scope. So these are applications that perform a single task on a single modality and will not perform anything outside of their scope. So when we were talking about the intracranial hemorrhage application on the last slide, that only works on a head CT for intracranial hemorrhage. It will not tell you if there is cerebral edema. It will not tell you if there's midline shift. It will not tell you if there is intracranial hemorrhage on a brain MRI. It is specifically a application for intracranial hemorrhage on CT. And then finally, we have radiomics. This is what we were referring to briefly as the holy grail, the next step for some of these AI applications. This technique has been referred to as a virtual biopsy, that we're able to go well beyond the human eye and what we're able to interpret and understand from a radiology image, and from imaging features alone, determine tumor pathology, potentially guide treatment, prognostication. So well beyond what we traditionally are able to accomplish with our own human eye radiologist interpretation of an image. Uh, the biggest feature or the biggest problem with the radiomics and the biggest limiting factor has been challenges in generalizability, and like we were mentioning earlier, the lack of multimodality or multi-specialty data. So there have been steps that have been taken to try to bridge this gap, take this next step, and this has been something that has been evolving over the past 5 years or longer. That it seems like it's going to be the next step very soon, but we still have these problems with broader application and with generalizability. So these are an example of two different types of papers that you'll see with this in the literature. And currently, this is limited to the research field and limited to small single institution or small multi-institution cohorts. But this will be something to keep an eye on in the near future as we continue to develop this technology. So those are the 10 core concepts of AI and radiology that we want you to keep in mind over the course of our lecture series. But we also recognize that this field of radiology AI continues to grow and continues to get more complicated. So as we have continued to do this course over the past 6 years, we've been collecting lectures, and we've been doing lectures on different topics. So if there's a topic that you are interested in, or if there is something that you think may be a gap in our curriculum, I would love for you to get in touch with me. Tell me what you would like us to cover in future courses. One area that we have covered in years prior was the use of LLMs, specifically ChatGPT, in radiology. So you can go through our course catalog and see if we've already done topics on something that you're interested in. But we value your feedback, and we would love to continue to make this course better. So very briefly, we'll go through some statistics and data preparation. So the three most common stats that you'll see in AI or in AI literature and AI papers will be the AUC ROC curves, Dice coefficients, and precision recall and accuracy. So the AUC ROC curves are going to be the plots of sensitivity and specificity. The important thing to remember about these graphs is that the closer that we get to a right angle that we're going up and across the top, the closer that we get to 1.0, the higher quality and the higher performance that we are seeing. So a lot of times we'll see these charting out, oh, how well is the AI application doing? How well is the human radiologist doing? And then how well are they doing it? Or are they doing a certain task together? So you might see, oh, the AI is doing not particularly well. It's about a 50%, or it's scoring about 0.5. And then you have a human radiologist who's maybe at 0.8, and then together they're 0.9. And that's just showing you that there's better performance and better outcomes with the human radiologist plus AI. The Dice coefficient is one of the common stats that you'll see for segmentation applications. So this is multiplying the overlap of two different regions, and then dividing them by the sum of the area of region 1 plus region 2. And this would be comparing sometimes a human standard of care or a human ground truth gold standard to the automated AI result. So the closer you are to 1.0, the better Dice coefficient, the better overlap you have. And then lastly, precision recall and accuracy. This is where you have your confusion matrix here with your true positives and true negatives, that you can calculate your recall, which is your sensitivity. Your precision is your positive predictive value, and your specificity is a different metric that we have here, and that's going to be your true negatives over your true negatives plus false positives. And accuracy is going to be a measure of your true and false positives compared to the total number of cases. So just as a reminder here, a high recall or a high sensitivity is going to be highly sensitive to positive findings. So you're going to detect a high proportion of the positive findings, but potentially at the cost of having a higher number of false positives. A high precision is a high likelihood that a positive result is truly positive. So this is going to have a higher proportion of positive results compared to your true and false positives. And high accuracy is a high likelihood that the AI result is correct. So both true positives and false positives. And then very briefly, we have a wide variety of data that we have to go through to be able to generate a viable AI application. Uh, Determining your sample size is very different, whether you just want to have a proof of concept, something you're doing at a single institution, versus something that you want to deploy commercially at multiple institutions. And there are different ways that we can augment our data. So this can be something that's important for relatively rare processes, so rare types of tumors, or something very specific that you're trying to generate an AI application. So you can take a single image, you can flip it in different ways, you can mirror reverse, you can increase or decrease the resolution, you can add grids. And this is more important for these very, very small data sets to try to increase the numbers that you have for developing your application and your training phase. And then lastly here, this will be the last thing that we talk about since we are well over time. It's very important to recall patient privacy. So having adequate management of the DICOM header, removing any patient identifiers. This includes name, date of birth, social security number, address, phone number, medical record number, accessor number. And something specific that we have to think about for neuroimaging is 3D facial reconstruction. So this is identifiable, and this is something that can be a big problem for a lot of these large data sets that we have to consider what types of anonymization tools are being used, and if we are publishing any data sets, that we have taken all the steps that we need so that we're not exposing patients' data. So that was a very rapid review of all of our fundamental concepts in AI. I hope that you'll be able to refer back to these as we're going through the week. And I hope that everyone has a fantastic week and welcome back to the AI literacy course. Thank you for your time.